For this component number 2 in chapter 12, which is a controller tuning relation. What does it mean? It means that to calculate the value of Kc, tau I, tau D using specific equation. Last time, when you do a direct synthesis method, you have to determine this. But here, you will just use it directly. Just use it. Okay? Just substitute the value and you get the value of Kc, tau I, and D. Okay, so the first one we have here is IMC tuning relation. Okay? IMC tuning relation, basically it came from the derivation, but don't worry, you don't have to derive that because it's a lot of things if you want to derive it. Okay, here we have this table. Okay, this is table 12.1. It is a IMC based controller setting, blah blah blah. I just want to tell you that when you have a model, a lot of models here, different type of model. When you have different type of model, which is G model, you can calculate the value of Kc, tau I, and tau D using this formula. Okay. Remember, last time we have second order plus time delay and first order. So if we have first order plus time delay, this is how to calculate the value of Kc. This is how to calculate the value of tau I. Okay, it's just about the same. Okay, we just put it like this. Put it as a Kc K, okay, equal to tau over tau C plus theta. So the Kc is equal to tau over tau C plus theta. Okay. I think it's just about the same. And tau I is equal to tau. Exactly the same as direct synthesis method. Okay. How about when we have a second order process? There is no second order plus time delay. Okay. Just second order without time delay. So this is the how to calculate the Kc, tau I, and tau D. Okay. So maybe we can go to an example. Okay. It will show you how to use this table. Okay, this is one of the example to show you how to use table 12.1. We have a model here, okay, with the value of k equal to 0.2, and we have to calculate the PI and PID controller setting, which is calculate the Kc tau I for PI controller, and for PID we have to calculate the value of Kc, tau I, and tau D. For tau C equal to 8 and tau C equal to 15. Okay, and we have to compare the response. Okay, so first thing, just take a look on the process model. Okay, our process model here, and then refer to table 12.1, which one is our process model. So it is M and N. Okay, it is M and N. So for PI controller, the value of Kc is equal to this. This is how to calculate the Kc. Okay, and this one is how to calculate the tau I. Same goes when we have PID controller. Okay, so this is the method to calculate the Kc, tau I, and tau D. Okay, let us calculate for the Kc for the first one. Okay, So the Kc for the first one, okay, this is the answer. So we try to calculate and compare with this answer. Okay. So for PI controller, okay, for PI controller, the KCK is equal to this one, 2 theta C plus 2 tau C plus theta, 2 tau C plus theta over tau C plus theta square. Okay, am I right? Okay, 2 tau C plus theta over tau C plus theta square. For tau I is equal to 2 theta C plus 2 tau C plus theta. Okay, and then we just substitute. Okay, we calculate for tau C equal to 8 first. 2, 8 plus theta. The value of theta basically is just took the theta equal to 7.4. Okay, don't need to take the negative. Okay, the negative no need to take. Just take the value. Okay, so we have 7.4 here divided 8 plus 7.4 square, and don't forget this side. You see Kc and 0.2 as our K. So the value of Kc you should get. Okay, anyone can calculate for me? Two times 8 plus 7.4 divided by 8 plus 7.4 square divided by 0.2. You will get 0.493, which is this one. Okay, so this is how to get the value. How about tau I? 2 times 8 plus 7.4. So it's equal to 16 plus 7.4. It's 23.4. Okay, so that is how to get this value. Okay, same goes when you have tau C equal to 15. You just change this into 15. Okay, you should get this value and this value. And then for the PID controller, okay, for the PID controller, okay, the formula to get KC is basically this one, right? Okay, 2 tau C plus theta over tau C plus theta over 2 square. Okay, so try to substitute. Did you get this value or not? This one and this one. Okay, for tau I is equal to same 2 tau C plus theta, 2 tau C plus theta. That's why you get the same value. And for the tau D, okay, just take this one. Okay, 2 tau C plus theta, and the above one, tau C theta plus theta over 4. Okay, square. So substitute the value of tau c, the value of theta, the value of k, and then you get this value of controller setting. Okay, controller setting means the value of kc, tau I, and tau d. That is a controller setting. Okay, so that is how we use table 12.1. Okay, and the question is very straightforward. Okay, just calculate the controller setting, refer to the table, search for the model, and use the formula directly. Okay, so this is the response when we get when we plug in the value of kc, tau I, and tau d into the system. This is the response that we get. The easiest way to get this response, basically you can use Simulink or MATLAB. You can use Simulink. Okay, you just plug in this one at PID controller. Okay, at PID controller, and it will result you this kind of response. Okay, so from these two response between PI and PID controller, which one is a better response? Which one is more favorable, more favor? How to determine which one is better? Anyone? Okay, of course no one, because I'm talking alone. You just listen, okay? Okay, so basically, in order for you to determine the response, whether which one is better, the first one, you, like I said, everything about characteristic of the response can be evaluated by calculating the, not the tau, calculate the rise time and settling time together with the overshoot. Okay, oscillation or overshoot. Okay, so here the simplest way is to calculate the rise time, the settling time. Okay, because the rise time is about the same. Okay, just about the same, only slightly different. So we find the difference. The difference between these two response is the the settling time. Okay, for the settling time of PI controller, this is PID controller. So for PI controller, the settling time is about here and here. Okay, but when you have PID controller, okay, the response for tau c equal to 8 is around here. Okay, for tau c equal to 8 is also around here. For tau c equal to 15, it's around here. Okay, about the same for tau. For PI, okay, it's basically we have 4 set of controller setting. Okay, we have a controller PI and PID. So each of the controller have different tau c. Okay, tau c different. Tau c equal to 8, tau c equal to 15. Okay, so between these 4, which one gives us the best response? Okay. To determine the best response, you should calculate the rise time, the settling time, not the rise time, and then you have to measure, roughly estimate the overshoot. Okay, as you can see here, PID controller have lower overshoot, compared to PI controller. Okay, and then what else? The difference. We can see the oscillation. Okay, the oscillation for PID controller is more because we can measure the number of peak. Okay, the number of peak is higher compared to the PI controller. Okay, so what are the answers? Okay, so this is the answer. The first one, we compare between tau c equal to 15 and tau c equal to 8 for both controller. Okay, we just compare. Okay, this line to this line, this line to this line, and for both controller, more sluggish and less oscillatory for tau c equal to 15. Okay, this dotted line, this dash line. This dash line for both controller have less oscillatory, less oscillation, and more sluggish. What does it mean by more sluggish? Sluggish means slow. Okay, it's more slow. Okay, if we can compare the rise time, it took slightly higher rise time in terms of rise time. In terms of settling time, also for this one, about higher than the tau c equal to 8. Okay, the settling time for tau c equal to 15 is higher than tau c equal to 8. Okay, the second one, okay, is divided into set point change and disturbance change. Okay, so this graph can be divided into two cases, whereby on a left side it is a set point change, and this one is a disturbance change. Okay. Previously, we have seen that a good controller should have a good disturbance rejection together with a good set point tracking. Okay, this is the meaning of set point tracking. When you introduce a step input like this, okay, a step input like this controller will bring back the system into this set point. Okay, and then when you introduce a disturbance, okay, this controller should be able to do a disturbance rejection, whereby it have to bring back the response into a set point. Okay, that is the definition of the set point tracking and disturbance rejection. So here in this case, for tau c equal to 15, okay, the overshoot is smaller, which is this one, and this one for set point change. Okay, for set point change, the overshoot is smaller. Okay, this one, overshoot is smaller. Okay, however, it have a large deviation after disturbance. This one. Okay, how big this line? Okay, this dash line, very big. Okay, compared to tau c equal to, we can compare this. Yeah, I know it's really messy here. Okay, I will delete something. Okay, so we can compare this area, okay, for the dash line, which is tau c equal to 15, compare with this one, which is smaller. Okay, this is the deviation. Okay, the deviation. Okay, same for both controller. Okay, for tau c equal to 15 compared to the tau c equal to 8, it's tau c equal to 15 have larger deviation. Okay, and then for the PID, it is a better response. Okay, it's a better response for disturbance because it's smaller. Okay, we can compare this. I put it A and this is B. Okay, A is smaller than B. We can see here the distance. Okay, A compared to B, A is lower than B. Okay, that's why PID controller, which is this one, have a better response. Okay, and then for the PID controller, it also have a short settling time. Okay, for tau c equal to 8. Okay, which is this one around here. Same goes here. Okay, as compared to tau c equal to 15. It took some time. Okay. So this is how to determine the response, whether it is a good response or not. What you need to do is you have to calculate the rise time, the settling time, and the deviation, the overshoot, the peak. Okay, which one is higher, which one is lower. Okay, then we can determine which of the response is a good response. Okay, don't get confused. A little bit theory, but you just give yourself time to digest. So you choose to be this line or this line, okay? Or this one. Good step 120. Okay. Okay. The next one is a tuning relation based on integral error criteria. This is another tuning method, tuning relation. Okay. Tuning relation means how to calculate the value of Kc, the value of tau I, and the value of tau d. Okay. So this chapter is all about these three things. Okay. Just about them. Okay, this chapter is just about them. How to calculate Kc, tau I, and tau d. Okay, this is another method whereby this is based on the error. Okay, the tuning based on the error. You don't have to think so much about it. Okay, just in a simple word that for this tuning PI or PID controller, for you to get the value of Kc, tau I, and tau d, we're going to use this formula. Okay, this formula and this value. Okay, don't worry, this is not in your CA. Okay, and then the third one, we have another equation, another tuning relation. Okay, this is another tuning relation. Again, it's just about the same like IMC table 12.1 previously, whereby when you have a model, this is how to calculate the Kc and tau I. So basically this one only cover for PI controller, not PID. Okay, and this one for when you have the model with a second order plus time delay. This is how to calculate the value of controller setting. Okay, also provided to meet to this condition. Okay, so I think we have done for the. Okay, this is one of the example. You can try by yourself. So for tuning relation is about an equation to find the value of Kc, tau I and tau D. You will be given a lot of equation. Okay, you don't have to derive. You just use the equation. Just plug in the number. Okay, make sure you know what is K, what is theta, what is a tau. Okay, this information you should get from a transfer function or from a G. Okay, this value, and then you plug in into any of the equation, and you will get this value. Okay, that is tuning relation all about. Okay, okay, this is a comparison of Ziegler-Nichols and Cohen-Kuhn equation. Just the same, whereby we have a different set of equation. This is Ziegler-Nichols, this is Cohen-Kuhn. Okay, so if the question came out in an exam or assignment, it should be a very direct question. Okay, very direct question, something like this. Okay, with a model given. Okay, with a given model, we just have to calculate the PI or PID controller setting using this method. Okay, so for PI controller, basically for Kc and tau I only. So you have to calculate this by using IMC. Okay, whereby the value of tau C is different. So just refer to the table 12.1, find the model, and then find the equation of Kc, K equal to what, tau I equal to what, then substitute the value of theta, the value of tau, and the value of K. This K, this is theta, this is tau. Substitute into this equation, you should get the value of Kc and tau I. Same goes for the C and D. Okay, just use the equation, just use the value. A very straight and direct equation. Okay. So this is what you should get. So you can try by yourself. Did you get this equation? Did you get this value or not?